Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight, we turn our gaze toward a gentle yet profound wondering. What if Earth was designed? Not in a hurried way, not with answers pressed upon us, but as a question we carry softly while drifting beneath the stars. The sky above us has been patient, stretching back over 13 billion years, waiting for us to look up and wonder. And so, together we ask, if our world bears the marks of design, what might those marks look like, and how would they whisper to us across deep time? If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. I wonder, where are you listening from tonight? Perhaps it's a small room with a dim lamp, or perhaps you're tucked beneath blankets as night falls. Whatever the hour and place, it belongs to you. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We begin at the simplest of thresholds, the velvet sky itself. Above us stretches a canvas that seems almost designed for awe. The human eye can perceive only a narrow band of light, yet that band happens to reveal stars, planets, and nebulae in a way that feels curated for beauty. It could simply be coincidence. Our biology arose under this sky, so of course our eyes match its glow. But still we wonder, might there be something deliberate in the harmony between our senses and the starlight they take in? The very darkness of night plays a part in this. If the cosmos were infinite, eternal and unchanging, then every point of the sky would blaze with starlight. Astronomers call this puzzle Olber's paradox. The resolution comes from the universe itself having a finite age and light needing time to travel. Darkness exists not because stars are absent, but because the cosmos has a horizon, a limit to what light has reached us. Without that veil of shadow, our nights would be unbearably bright. Darkness then becomes a gift. It is the quiet backdrop that allows us to sleep, to dream, to wonder. Was that necessary for life like ours, or does it feel designed only because we depend on it? In this early stillness of thought, we might linger on one detail, the colour of the sky. By day it is blue, by night, black. That contrast arises from air scattering sunlight, from molecules small enough to spread blue light more than red. Had our atmosphere been thicker, the sky would be perpetually hazy, the stars hidden even in darkness. Had it been thinner, harsh radiation would reach the ground unchecked. The delicate balance between transparency and protection seems almost tuned for life to gaze outward while remaining safe below. Is it design, or is it simply one outcome of countless possibilities across the vastness? Astrophysicists often remind us of the anthropic principle, a quiet thought that says, we observe this universe because it permits observers. If conditions were not favourable, no one would be here to notice. Still, the idea lingers that our environment fits us with unusual precision. Earth rotates at a pace that grants us gentle day and restful night. Too fast and storms would tear across the continents. Too slow and heat would burn one side while cold froze the other. The length of our day seems almost chosen, a rhythm set for life's heartbeat. In the silence of the cosmos, there is a fact worth carrying gently. The human brain, at rest, generates waves of electricity that drift at about the same rhythm as ocean tides and circadian cycles. The body hums to a tempo shaped by Earth's rotation and the pull of its moon. Was this convergence inevitable, or is it the faint echo of something designed? We might also recall the stars themselves. The night sky we see is not permanent, but fleeting. Stars have shifted over time, constellations reshaped as they drift across the galaxy. Yet from our point of view, they trace recognizable patterns simple enough that early humans wove them into stories. Orion, the hunter, always stands tall with his belt of 3. The Big Dipper forever points to Polaris, the North Star, guiding wanderers through the centuries. It could be random alignment. But the way these points of light form enduring guides for navigation feels like an open invitation to notice. And then there is the quieter truth. Most stars in the Milky Way are not like our Sun. Many are cooler, redder dwarfs, burning faintly for trillions of years. A few are hotter giants, blazing bright but short-lived. Our Sun sits in the middle, a star stable enough to shine gently for billions of years. That steadiness has given Earth time to nurture forests, oceans, and us. We may call it chance, but it feels like design when seen from beneath the velvet sky. Astrophysicists still debate whether the constants of physics, the strength of gravity, the charge of the electron, the speed of light, could have been otherwise. If they were even slightly different, stars might not form, chemistry might collapse, life might never stir. Perhaps these numbers are inevitable, locked by some deeper law, or perhaps they are one set among many possible, with Earth appearing as a rare haven in a multiverse of silent worlds. Either way, to lie beneath the night sky is to feel the quiet weight of those numbers pressing gently upon us, as though stitched into the fabric of existence with care. As we drift into this thought, we can feel ourselves settling. The universe does not answer whether Earth was designed, but it offers images that hint, tease, and lull. A sky that darkens just enough for rest, a day that lasts just long enough for balance, a sun that burns just gently enough for billions of years. Coincidence or craft? We cannot know. But the question itself carries us like a slow tide beneath the stars. After floating beneath the velvet dome of night, we find ourselves drifting backward in time, past the stars, past the galaxies, all the way to the beginning of the light itself, the cosmic dawn. It was here, in the deep hush after the Big Bang, that the first whispers of structure began. A faint glow spread across the young universe, gentle and uneven, like a veil lit by distant embers. We often speak of this era with reverence. The first time light had somewhere to go. The cosmic dawn was not a sudden burst. It was a slow unveiling, a gradual breaking of a long and silent night. For nearly 400,000 years after the universe began, it was too hot, too dense, too chaotic for light to travel freely. Protons and electrons collided constantly, forming a fog that blocked all vision. Then, as the universe expanded and cooled, atoms formed, mostly hydrogen with a trace of helium, and light was finally free to move. This moment is known as recombination, though in truth it was the first combination, the birth of transparency. That ancient light still travels, stretched by the expansion of space. We now call it the cosmic microwave background, the oldest light we can see, glowing faintly in every direction. To us, it appears as a uniform wash, but hidden within it are tiny fluctuations, small ripples that would seed the entire cosmic web. Some scientists wonder, if Earth was designed, could these fluctuations have been tuned? Were they the fingerprints of intention written across the newborn sky? The fluctuations are incredibly precise, differences in temperature of only 1 part in 100,000. And yet those differences allowed matter to clump, collapse, and eventually give rise to galaxies, stars, and planets. Without them, the universe might remain a smooth fog, with no structure, no chemistry, no us. It's tempting to ask whether this initial pattern was sculpted with purpose, or whether randomness simply stumbled upon the right conditions. As we drift gently through these early moments, another faint glow calls to us, the light from the first stars. They were massive and short-lived, burning hot with ultraviolet light that rionized the cosmos, stripping electrons from atoms once more. This period is called the Epoch of Rionization, a second kind of unveiling, where darkness lifted again and the universe became clear. These early stars were different from the ones we see today. They were made of pure hydrogen and helium, no heavier elements yet. Astronomers call them population 3 stars, and they've never been directly observed. They may have burned briefly and brilliantly, then vanished, leaving behind black holes or supernovae to spread the first elements needed for future worlds. If there was design in these early fires, it was a quiet kind. Not a blueprint etched in stone, but a whisper in the balance between collapse and explosion, between fusion and gravity. These first stars did not last long, but they made everything else possible. Gold, carbon, oxygen, iron, all of it forged in the hearts of these primordial giants. From their brief lives came the raw material for planets, oceans, and breath. There is something deeply poetic in that, light from the beginning, creating the seeds of structure, only to fade. Could a designer, if such a presence existed, have planned a cosmos where early brilliance was not the goal, but the means? A quiet prologue before the symphony. Even now, telescopes like the James Webb Space Telescope peer into these distant epochs, searching for faint galaxies at the edge of the observable universe. What we see are not the galaxies as they are, but as they were billions of years ago. The further we look, the younger the cosmos appears. It's like gazing into a time-sculpted mirror, each reflection deeper than the last. What we find there often surprises us. Galaxies that formed earlier than expected. Stars with unusual compositions, massive structures in places they shouldn't be, at least not according to the models we've built. Astrophysicists still debate whether our understanding of early structure formation is complete. If Earth was designed, perhaps the clues lie not in our world, but in the silent architecture of those early lights. There's also a mystery in symmetry. The universe, on large scales, appears remarkably even. Galaxies are not all clumped in one region, nor are they drifting apart at random. Instead, they form a kind of filamentary lacework, a cosmic web. Matter gathered where the early fluctuations were densest, creating a structure that spans hundreds of millions of light years. Filaments of galaxies thread across the darkness, with vast voids between them. And yet, there is no central point, no preferred direction. The universe has no top or bottom, no edge or middle. It expands everywhere, evenly, as if the rules were written with an elegant impartiality. Is this the signature of randomness guided by physics, or the careful hand of something we can't quite name? There's a lesser-known detail about the cosmic microwave background that feels almost like a nudge, a faint anomaly, an asymmetry across the sky, sometimes called the axis of evil. It's likely a statistical fluke, or perhaps an unknown foreground effect. But its presence lingers, as if inviting us to look again. Scientists are cautious, of course. Patterns can mislead, and coincidence often dresses itself in meaning. But in the quiet hours, the question remains. We can imagine a universe like a canvas, and the cosmic dawn as the first brushstroke. Not detailed, not finished, but filled with potential, a simple scattering of light and matter, and from it, everything to come. There's no final answer here, just the drift of thought, the hush of observation, and the light of ancient stars falling gently across time. Let us drift now into the shape of the universe itself, into its vast geometry and slow unfolding. Imagine a cosmos not simply vast in distance, but rich in form. One of the gentlest questions cosmologists ask is whether space has a shape, and if it does, was it chosen? Not all space is the same. Geometry on the grandest scales bends and curves depending on mass, energy, and the rules of expansion. And so we find three possible shapes: closed like a sphere, flat like an endless plane, or open like a saddle curving outward forever. These aren't visible curves, not like the arc of a planet or the ripple of a hill, but subtle warps written into the background of space-time itself. Observations from the cosmic microwave background suggest that the universe is remarkably flat. Not perfectly, perhaps, but close enough that any curvature would only reveal itself far beyond our visible horizon. If it were any more curved, galaxies might have collapsed in on themselves long ago. If less, matter might have thinned out too quickly to form stars. It's a delicate middle, a balance point between chaos and stillness. Was that balance chosen? The early universe expanded with incredible speed. In a fraction of a second after the Big Bang, space itself ballooned in what we call cosmic inflation. This expansion smoothed out irregularities, flattened geometry, and erased primordial wrinkles. Some physicists suggest this was simply the nature of early fields and quantum fluctuations. Others wonder whether inflation itself might have been tuned. A cosmic dial turned just so, yielding a universe where galaxies could bloom. One fascinating detail emerges here. Inflation didn't just make the universe large, it made it uniform across regions that could never have communicated. Imagine two parts of the sky, so far apart that light hasn't had time to pass between them, and yet they match in temperature to an astonishing degree. Some say inflation stretched a small connected patch into the cosmos we see today. Others whisper that it might mean more than that. Could a designed cosmos begin with just enough chaos to make patterns meaningful? We find ourselves surrounded by parameters that feel placed with care. The density of matter, for example, plays a quiet but crucial role. Too dense, and the universe collapses back on itself. Too sparse, and galaxies never form. The observed value sits near a threshold called the critical density. It's as if the universe threads a needle between fire and void. And then there is dark energy, the unseen force pushing the cosmos apart. Its strength is faint, yet its influence is vast. Without it, the expansion would have slowed more rapidly. With more of it, structure might never have formed. Its value, too, lies in a narrow band. Physicists still debate what dark energy is, or if it's a placeholder for something deeper. Some suspect it's part of a quantum vacuum. Others wonder if it's evidence of design, a slight breath woven into the fabric of space. Here we might pause and recall that geometry has no edge. In a flat or open universe, you can travel forever and never reach a boundary. Yet you may also return where you started, as in some models of finite but unbounded space. Like walking across the surface of a sphere, you could go on without ever finding a wall. Such an idea is difficult to picture, but beautiful in its own way. A cosmos without edges, but also without ends. If Earth was designed, it exists not on the rim of a cosmos, but within something deeply connected. No front, no back, no center, just endless unfolding. There's another thought worth carrying. Our observable universe is not the whole of everything. It's merely the region from which light has had time to reach us. Beyond it, space likely continues, perhaps forever. If there is design, it may lie beyond even our most patient gaze, just outside the reach of ancient photons, a frontier of mystery that hums softly at the edge of our knowing. Some lesser-known models propose that what we call the Big Bang was not a beginning, but a transition, a ripple in a higher dimensional space, or a rebound from a prior collapse. In some theories, the multiverse is not a poetic fancy, but a consequence of inflation itself, each region expanding into its own bubble, with its own rules. If so, Earth's quiet design could be one thread in a vast and varied loom. Still, the flatness of our own region, the quiet harmony of forces and the way time flows in one direction, all feel strangely gentle, like rules chosen for peace. And what of time? The universe has direction. Entropy, the measure of disorder, always increases. From hot and simple beginnings, we flow toward complexity and coolness. Galaxies, stars, planets, and minds all emerge in the low entropy past and drift into the high entropy future. Time, it seems, is an arrow, and its path has allowed consciousness to bloom, if only briefly. Why should this be so? We don't know. Physicists still debate why time has a direction at all. The equations of nature are symmetrical. They work equally well in reverse. Yet our experience is not symmetrical. We remember the past. We don't remember the future. We fall downward, not upward. We age. Was this asymmetry built into the design? If Earth was placed with care, then perhaps time was too. Not as a prison, but as a garden that grows and withers and rests. And so we glide through this gentle inquiry, not to solve it, but to live inside it for a while. A flat universe with quiet curvature, a horizon that hides more than it shows, a beginning wrapped in silence. These are the forms of our cosmos, not hard-edged or glaring, but soft, spacious, and deeply still. Let's continue our slow drift outward, this time into the grand lacework of the cosmos, a structure so vast, so quiet that it almost feels too delicate to be real. And yet it's there, woven across billions of light years. Astronomers call it the cosmic web, and it is perhaps the largest known structure in the universe. When we map the positions of galaxies, we don't see a random scatter. We see filaments, threads of clustered galaxies, stretching like bridges across darkness. Between them lie enormous voids, vast and empty regions where almost no galaxies dwell. Together these filaments and voids form a kind of scaffolding, as though the universe followed an invisible pattern laid down long ago. This web wasn't carved by hand, of course. It emerged from gravity, pulling matter toward the densest regions seeded by those tiny fluctuations in the early universe. And yet, its elegance stirs something in us. Why should galaxies trace such graceful arcs? Why should they thread themselves together like beads on a string? Some wonder if these structures reflect the shape of the initial quantum fluctuations, stretched and amplified by inflation. Others suspect the presence of dark matter, forming the silent frame upon which visible matter gathers. Dark matter itself is still mysterious. We cannot see it, cannot touch it, but its gravity pulls on galaxies, keeps clusters from flying apart, and sculpts the web. If the universe were truly chaotic without hidden laws, would such a pattern emerge? Perhaps. Randomness can yield beauty, given enough time and scale. But this web feels more like rhythm than noise, like a melody heard faintly through static. We might pause here to picture one of the lesser-known wonders nestled inside this web, the Bootes Void, a spherical region nearly 330 million light-years across, containing almost nothing. Only a few scattered galaxies float within it, lonely islands in a dark sea. Its emptiness is startling. Some have called it a cosmic desert, others a question without a voice. Was this silence designed? Or is it the absence of design, the echo of randomness? Even within this vast framework, not all galaxies are the same. Some are brilliant spirals, like our Milky Way, with swirling arms that birth new stars. Others are ellipticals, smooth, quiet, filled with older stars. But there's another kind, the ultra-diffuse galaxies. These are ghostly realms, galaxies as large as the Milky Way, but with far fewer stars. They're dim, spread out, and strangely fragile looking, like cosmic breath on glass. Ultra-diffuse galaxies challenge our ideas. How do such faint structures form? How do they hold themselves together? Some seem to lack dark matter entirely, a detail that doesn't quite fit with the standard models. Others cling to clusters, as if shaped by the tidal forces of larger neighbours. Their presence is a gentle puzzle. Perhaps they are accidents. Perhaps they are whispers of something else. We can also drift into the quiet companionship of globular clusters, dense spherical swarms of stars that orbit the outskirts of galaxies. The Milky Way hosts over 150 of them. They're among the oldest things we can see. They're stars formed in the early chapters of the universe. Unlike the thin disk of our galaxy, these clusters are compact and ancient, like lanterns still flickering from the cosmic dawn. Some astronomers think they may be relics of the first galaxies, long since absorbed. Others believe they formed in the collapsing halos of dark matter. Still others wonder whether they hold clues to conditions that favoured planetary formation, or even life. In their silence, these clusters feel almost contemplative, suspended between the stars and the void. And then there are the gravitational dances of galaxy clusters themselves, vast gatherings of hundreds or thousands of galaxies bound together by gravity. Within them lies another quiet player, hot gas, invisible light but glowing in X-rays. This gas fills the spaces between galaxies, holding more mass than all the stars combined. It is this hot intra-cluster gas that allows us to glimpse a phenomenon known as gravitational lensing, a bending of light caused by mass. As light from distant galaxies passes through these clusters, it bends, warps, and sometimes duplicates the image. We see arcs, rings, and echoes, illusions drawn by gravity itself. It's a stunning confirmation of general relativity, but also a cosmic reminder. Light does not always travel straight. Space can curve, and so can the story it tells. Some lensing is strong, producing dramatic shapes. Other times it's weak, revealing subtle distortions that require careful analysis. But always, it is the mass, much of it dark and hidden, that sculpts the path of light. A silent sculptor shaping ancient photons as they fall toward us. Astrophysicists still debate the full nature of these lenses. Could they reveal unseen structures? Could they help us map the invisible frame of the cosmos? Perhaps. Or perhaps they are only a side effect of mass and distance. But to see the same galaxy repeated, its light bent into a curve, feels like stumbling across a note written in gravity's hand. And so, the cosmic web becomes more than filaments and voids. It becomes a kind of gentle infrastructure, holding galaxies like dew on a spider's thread. A slow dance of light and mass, a quiet interplay of seen and unseen. If Earth was designed, perhaps the design stretches beyond our world. Perhaps it lies in the space between galaxies, in the arrangement of voids, the softness of curves, the silence of shadows. Or perhaps we are simply drawn to pattern, to symmetry, to the illusion of meaning written in structure. That too is beautiful. For now, we drift in this web, not caught, but suspended, listening to the hum of galaxies, watching the way light bends, and wondering, not urgently but gently, whether this vastness carries the echo of something intended. From the sweeping scaffolding of galaxies, we now slow our pace and drift closer to the gentle glow of starlight, into the quiet forges where stars are born, live, and softly fade. If Earth were designed, perhaps it is here, in the slow breathing of stars, that we might glimpse the first brushstrokes of that design. Stars begin not in fire but in darkness. Within cold, dense clouds of gas and dust something stirs. These are molecular clouds, vast and veiled, where the temperatures fall low enough for hydrogen molecules to cling together. In these quiet nurseries, gravity works slowly, gathering matter into knots, then pulling tighter and tighter until pressure and heat ignite nuclear fusion. A star is born not with noise, but with a soft flicker of light that deepens over time. One such cloud is the Taurus molecular cloud, relatively nearby in cosmic terms. It hosts hundreds of infant stars still wrapped in their cocoons of dust, their light barely breaking through. Instruments like ALMA and the James Webb Space Telescope let us peer into these regions, revealing disks of matter spinning around young stars, places where planets may one day take shape. These protoplanetary disks are delicate, chaotic, and full of potential. Swirls of gas and dust collide, clump, and merge. Over millions of years they may settle into rings and form rocky worlds, gas giants, icy moons. Each star, each disk, a new laboratory for creation. And yet, Many of these efforts fail. Some systems fling their planets into space. Others collapse inward or never quite cohere. But sometimes, just sometimes, a world like Earth appears. Was this the result of cosmic patience, or was something more deliberate at work? It's easy to imagine chaos at this scale. The sheer number of failed systems dwarfs those that succeed. But there's a quiet order, too, a sense that physical laws guide each step with surprising gentleness. The conservation of angular momentum causes disks to flatten. Radiation pressure balances gravitational pull. Accretion flows inward, while winds blow outward. Even chaos seems to obey a kind of rhythm. Our own sun emerged this way, born from a cloud about 4.6 billion years ago. Around it spun a disk of dust and gas, the leftovers of formation. From that material came Earth, and the Moon, and all the planets we now know by name. The same elements forged in earlier stars, carbon, nitrogen, oxygen, iron, became the ingredients of oceans, of trees, of breath. The very atoms in your body were once inside stars. In this sense, the cosmos is not just the stage, we are part of the performance. And yet, how many such stars, how many disks, how many worlds must have formed before a planet like Earth came into being? Perhaps billions, perhaps more. Astronomers still debate how rare Earth truly is. The rare Earth hypothesis suggests that many factors had to align just right. A stable star, a circular orbit, a protective magnetic field, nearby gas giants to deflect comets, plate tectonics to recycle carbon, and liquid water sustained over eons. None of these alone is miraculous, but together they form a stack of improbabilities. Was it chance or choreography? We might also reflect on a lesser-known detail, the snow line. In every protoplanetary disk there exists a boundary beyond which water freezes. This is the snow line. Inside it, rocky planets tend to form. Beyond it, gas giants and icy worlds take shape. Earth lies just inside that boundary, close enough to remain warm, far enough to avoid being swallowed by its star. If Earth had formed a little farther out, it might be a frozen wasteland. A little closer, and it might have been scorched like Mercury. Its placement seems gentle, balanced, precise. And then there's the remarkable chemistry of carbon. It forms long, stable chains, ideal for life. It bonds easily with hydrogen, oxygen, nitrogen, elements common in the universe. Silicon, though abundant, doesn't share this flexibility. Life, as we know it, is carbon-based, not just because carbon is available, but because its properties seem almost designed for complexity. Still, we must be careful with words like designed. The universe is full of surprises. We know of exoplanets orbiting twin suns, planets with days that last longer than their years, worlds tidally locked, with one side forever in sunlight, the other in darkness. Some of these planets lie within the habitable zone, the narrow region where temperatures might allow liquid water, and so the gallery of possible Earths expands. But Earth is not just habitable, it is steadily habitable. Over billions of years, despite asteroid impacts, climate swings and drifting continents, it has remained within a range that nurtures life. Was this luck, resilience, or a product of deeper tuning? One lesser-known stabilizer is the presence of Jupiter. The gas giant acts as a kind of guardian, its immense gravity redirecting many incoming comets and asteroids. Without it, Earth might have suffered far more frequent collisions, too many for life to persist. And yet, had Jupiter been larger or closer, it could have destabilized Earth's orbit instead. The placement of planets in our solar system feels like a quiet harmony. Each orbit a note, each planet a different tone. Not a perfect symphony, but something close enough to be remembered. And so we look again at our Sun. It is not the brightest, nor the largest. It is a G-type main sequence star, modest in size and output. But it is stable. It doesn't flare wildly or dim unexpectedly. Its spectrum allows for photosynthesis. Its lifespan is long enough to allow life not just to emerge, but to evolve. Some stars burn through their fuel in a few million years, far too fast for life to find a foothold. Others flicker weakly, casting red light that may not penetrate thick atmospheres. Our sun sits in the middle, ordinary in many ways but quietly extraordinary in its reliability. Astrophysicists still explore whether this kind of star is common enough to host many Earth-like worlds, or whether Earth is a rare island in a vast and stormy ocean. But when we lie back and feel the sun's warmth on our skin, it's hard not to wonder if that warmth was made for more than just light. If Earth was designed, perhaps it began here, in the disks around young stars, in the fusion within suns, in the gentle laws that guide collapse and creation, not as a grand declaration, but as a soft whisper, a breath that became warmth, a warmth that became home. We followed starlight from its earliest flickers to the quiet forming of our sun. Now let's linger on Earth itself, our quiet cradle, suspended in the dark, orbiting a modest star in a vast and whispering cosmos. What makes Earth feel chosen? It could be the way it moves, its slow rotation, giving us days just long enough for light and sleep, its tilted axis producing gentle seasons that stir life into rhythm, its elliptical orbit not too stretched, not too circular, balancing distance and warmth. These traits could be the result of random collisions and cosmic chaos, but taken together, they feel almost tuned. Like a song composed not all at once, but note by note over eons. One mainstream fact worth carrying gently is Earth's axial tilt, 23.5 degrees. That simple angle creates the seasons. Without it, the poles might freeze eternally, and the equator bake without relief. With too much tilt, the swings between summer and winter would be violent, destabilizing the climate. The tilt itself is not fixed. It wobbles over tens of thousands of years, but the range is steady enough to keep Earth's rhythm intact. A lesser-known detail is that this tilt is stabilized by the Moon. Without our Moon, Earth would likely wobble chaotically, its axis drifting dramatically over time. That would wreak havoc on climate cycles, making the long-term stability of life much harder. The Moon, by tugging gently at Earth's bulge, acts as a kind of gravitational anchor. Was it placed there deliberately? Or was it a miraculous consequence of ancient violence? The Moon's origin is itself a mystery, though many scientists support the giant impact hypothesis. According to this model, a Mars-sized body struck the young Earth, flinging debris into orbit. That debris coalesced into the Moon. It was a violent event, but the aftermath shaped everything. The Earth's rotation sped up. The tilt stabilized. The oceans began to feel the pulse of tides. Life, when it came, would learn to follow that rhythm. The Moon's size is unusually large relative to Earth, far larger than typical planetary moons, and it sits at just the right distance to create total solar eclipses, where its disk perfectly covers the Sun. From Earth's surface, the Sun and Moon appear almost the same size in the sky. This is a coincidence, perhaps, but it's one that allows us to study the Sun's corona, to witness the layers of starlight that would otherwise remain hidden. If Earth was designed, did it include a moon that could both stabilize its dance and peel back the veil on the star that gives it life? Even Earth's surface tells a story of balance. Plate tectonics, for instance, recycle carbon, shape continents, and regulate climate over geologic time. Without them, carbon dioxide would build in the atmosphere or vanish into rock, sending the planet into deep freeze or runaway heat. But Earth's crust is fractured just enough to move, driven by inner heat, cooled by water. Astrobiologists still debate how rare plate tectonics might be. We haven't yet confirmed them on other planets. Mars has none today. Venus may once have had them, but now lies locked beneath a stagnant lid. Perhaps Earth's tectonic churn is an accident, or perhaps it was essential, and water, so abundant, so quiet. It covers over 70% of Earth's surface. It moderates temperature, transports nutrients, dissolves minerals and carries life. Liquid water is rare in the universe, at least on planetary surfaces. Too close to a star and it boils away. Too far and it freezes. But Earth orbits in a region sometimes called the Goldilocks zone. Not too hot, not too cold. Even the thickness of our atmosphere feels quietly ideal. Thin enough to let in light, thick enough to trap warmth, oxygen-rich yet buffered by nitrogen, not too corrosive, not too inert. The ozone layer filters harmful radiation. Magnetic fields shield us from solar winds. Each layer, each field, each boundary, soft walls protecting a garden. But Earth is not perfect. Storms rage, volcanoes erupt, ice ages come and go, and yet life adapts, rebuilds, continues. Perhaps perfection was not the goal. Perhaps beauty lies in resilience, not control. One quiet debate in planetary science is whether Earth's magnetic field is a necessity for life. It protects our atmosphere from being stripped by solar winds. Mars, once likely wet, lost its magnetic field and then its air. Earth's field is generated by its molten iron core, spinning beneath the crust like a quiet dynamo. Could life exist without such protection? Maybe. But here, we have it, a silent shield. And then, there's the presence of continents and oceans, not just in their existence, but in their distribution. The arrangement of land and sea affects wind patterns, ocean currents, climate cycles. If continents were bunched into one hemisphere, the seasonal swings would be severe. If oceans were deeper, land might be scarce. Earth seems to offer just enough dry ground to build civilizations, and just enough sea to cradle climate. A lesser-known pattern is the Great Ocean Conveyor Belt, a global current that carries heat from equator to pole. It keeps the tropics from boiling, and the poles from freezing further. It helps distribute nutrients and regulate the breathing of the ocean. This conveyor is driven by temperature, salinity, and wind. It is slow, steady, and crucial. Disrupt it, and the world changes. So we look around and ask softly, is this a planet born of blind chance or of quiet structure? We can never be sure, but what we can do is notice the tides that rock us to sleep, the air that fills our lungs without flame, the ground that holds us gently, the sky that darkens just in time to rest. Perhaps the design lies not in perfection, but in suitability, in a world that doesn't eliminate challenge, but balances it with beauty. A world that cradles life, not by force, but by form. Earth, then, might not be a masterpiece, but a garden, a place shaped by time, by fire, by accident, and maybe by care. Let us wander now toward water, not just the still blue oceans or the soft rain against windows, but water in all its forms, ice clinging to polar caps, vapour curling into clouds, rivers carving stone. Water is not merely a feature of Earth, it is a quiet architect, shaping every contour, nourishing every root, whispering through every breath. It's easy to take water for granted, yet in the cosmic context, it is rare to find so much of it in liquid form. Water is abundant in the universe. It forms easily from hydrogen and oxygen, both common elements. But liquid water, that requires a delicate balance of pressure and temperature. Too much heat, and it boils away. Too little, and it locks into ice. Earth, alone in our solar system, sits in that narrow middle. One mainstream truth is this: water is essential to life as we know it. Every cell, every system in our bodies depends on it. It dissolves nutrients, transports signals, regulates temperature. Without water, DNA cannot fold, proteins cannot move, life cannot spark. It is the medium of life and the canvas upon which life paints its forms. A lesser-known feature of water is its anomalous expansion when freezing. Most substances contract as they freeze. Water unusually expands. This makes ice less dense than liquid water, so it floats. Imagine a world where it didn't. Lakes and oceans would freeze from the bottom up, locking into solid masses, killing everything beneath. But on Earth, ice forms a protective shell, insulating the water below, allowing life to endure even in the harshest cold. This simple reversal, floating ice, might seem minor, but it's a quiet key to Earth's long-term habitability. Without it, entire ecosystems would collapse in winter. With it, life persists through cycles of cold and warmth. Could that property be an accident? Perhaps, or perhaps, if Earth was designed, this was a quiet refinement, one that invites life not just to exist, but to flourish through time. We might also drift toward Earth's hydrological cycle, the movement of water through evaporation, condensation, precipitation, and runoff. It is an endless, unhurried loop, powered by sunlight and gravity. Oceans give rise to clouds, clouds give birth to rain, and rain returns to sea. This cycle regulates temperature, distributes nutrients, shapes landscapes. It connects mountain and ocean, ski and soil. The elegance of the water cycle is not just in its function, but in its softness. There is no harsh extraction, no violent renewal, just the slow rise of vapour, the drifting of clouds, the falling of drops. It feels almost mindful. Astrophysicists and planetary scientists still debate how Earth's water arrived. Some argue it formed in place, trapped in minerals during Earth formation. Others believe it came from beyond, delivered by comets or asteroids carrying icy cargo from the outer solar system. Either way, the timing and quantity had to be just right. Too little water, and Earth would be barren. Too much, and land would vanish beneath endless oceans. Even here, balance seems to emerge. Earth's oceans also serve as long-term carbon regulators. Carbon dioxide dissolves into seawater, forming carbonic acid, which interacts with rocks and sediments. Over time, this process helps stabilize the climate. Volcanic eruptions add carbon, while weathering and the ocean remove it. It's not a fast system, it works over millions of years, but it's another quiet loop, another form of balance. A lesser-known contributor to this balance lies in subduction zones. As tectonic plates shift, oceanic crust is pushed beneath continental plates, carrying carbon-rich sediments into the mantle. There, some of it is returned via volcanic eruptions. This deep carbon cycle helps keep atmospheric conditions suitable for life, long after surface changes would otherwise throw it off course. Once again, we see design not in perfection, but in interconnection. Water does not act alone. It partners with rock, wind, gravity, and heat. Together, they create a planet that breathes. And then there are rivers. Rivers carve valleys, shape deltas, move life from mountaintop to sea. They carry minerals, nurture forests, and create fertile ground for agriculture. Civilizations have always bloomed beside them. The Nile, the Tigris, the Yangtze. Rivers are not just natural features, they are histories. Many rivers follow winding, meandering paths. These curves aren't random. They emerge from feedback between flow speed, sediment, and channel shape. Over time, rivers self-correct, changing course, sometimes forming oxbow lakes. The meander, like so much else on Earth, is a compromise between energy and resistance. It's how water whispers its way through time. And then there's rain. Rain falls on us not with urgency, but rhythm. It comes from clouds shaped by invisible currents, born of sunlight warming the sea. Rain nourishes crops, fills aquifers, cools the land. But it also speaks to something gentler, a renewal that asks nothing, a rhythm that arrives and fades. We might also notice fog, mist curling over valleys at dawn, dew on grass, the condensation of vapour into tiny droplets, each as a phase of water, softening the air, easing the heat, bringing stillness. And beneath the surface in the dark lie aquifers, underground rivers and reservoirs held in porous rock. They feed springs, sustain dry regions, and hold water that may have fallen thousands of years ago. Water, then, is not just present. It is stored, cycled, protected. Could all of this have emerged by chance? Perhaps. But when we view the hydrological cycle, the chemistry of ice, the slow loops of carbon and heat, and the quiet rivers of the deep earth, it feels like a system not of accident, but of purpose. Not loud, but laced with care. Astrobiologists look for signs of liquid water on other worlds as a leading indicator of habitability. Mars shows evidence of ancient lakes. Europa and Enceladus harbour subsurface oceans. Even distant exoplanets are scanned for watery fingerprints. But Earth, so far, remains unique in its wealth of liquid water on the surface under breathable air, beside green land. It is a planet that moves like a poem, slow, layered and gentle, and water is the ink. If Earth was designed, water may have been the first tool. A solvent, a sculptor, a song. It falls, flows, freezes, melts. It carries life and remembers shape. It listens. Now we float gently towards something both familiar and quietly astonishing. The presence of Earth's companion, the moon, a pale, faithful sentinel, always facing us with the same soft gaze. If Earth were designed, it is hard to imagine that the moon wasn't part of the intention. It hangs there, perfectly round to our eyes, waxing and waning with slow rhythm. It reflects sunlight, diffused into silver. It pulls on the oceans, stirs the tides, and marks the passage of time. Its presence is so constant that we often forget how rare such a relationship might be. Among the planets of our solar system, Earth is unique in hosting a moon so large relative to its own size. Most other moons are tiny, captured rocks or icy fragments. But our moon is massive, nearly a quarter of the diameter of Earth, with enough gravity to shape not just tides, but time itself. One mainstream fact is this: the moon's gravitational pull creates tidal bulges in Earth's oceans, causing high and low tides to rise and fall in a regular rhythm. These tides affect marine ecosystems, migration patterns, and even climate. Early life likely depended on these gentle shifts. Tidal pools filling and drying, concentrating nutrients, perhaps giving rise to the first cellular experiments in complexity. The moon doesn't just move water, it subtly pulls on Earth's crust, generating tiny tremors known as Earth tides. It slows Earth's rotation over time, lengthening the day by a few milliseconds every century. Long ago, a day was only 6 hours long. Today, it stretches past 24. This gradual deceleration may have given life the time it needed to evolve. More time for sleep, for photosynthesis, for balance. A lesser-known detail is the way the moon stabilizes Earth's axial tilt. Left to itself, Earth would wobble wildly, its seasons shifting over thousands of years in unpredictable ways. But the moon, with its quiet tug, acts like a counterweight. It keeps Earth's tilt within a narrow, stable range. That consistency may have been critical for long-term habitability. Without the moon, Earth's climate might have been too chaotic for complex life to take root. Forests might never have spread. Ice ages might have arrived too violently. Stability, it seems, is one of the softest signatures of care. Astronomers still study the moon's origin, and though the giant impact hypothesis remains the leading theory, there are uncertainties. If a Mars-sized body struck Earth and created the moon, why do both bodies share nearly identical isotopic compositions? Some suggest a more complex collision, others propose a slower merging. A few wonder whether we're still missing part of the story. The moon's synchronous rotation, always showing the same face, is the result of tidal locking, a process that takes millions of years. At first, the moon spun freely, but Earth's gravity tugged on it unevenly, creating internal friction that gradually slowed its spin until it matched its orbit. Now, one side always faces Earth, the other, the so-called far side, remains hidden until we send spacecraft to glimpse it. There is something poetic about this locked gaze. The moon watches us, but only with half its face, a reminder perhaps that even in design there are shadows. We often marvel at eclipses, especially total solar eclipses, where the moon perfectly blocks the sun. It is a rare alignment made possible because the moon is 400 times smaller than the sun and 400 times closer to Earth. This coincidence, or this proportion, means the sun and moon appear nearly identical in size from our point of view. During a total eclipse, day becomes night, birds fall silent, stars emerge in midday. And we glimpse the sun's corona, its faint glowing halo. Without eclipses, this structure would remain invisible, but because of the moon's exact size and distance, we see the sun's outer atmosphere revealed in soft white loops. Could this be an accident? Most likely. But if Earth were designed, this alignment might feel like a moment of intentional unveiling, a curtain briefly drawn back to reveal what lies behind the light. The moon has shaped not only biology and climate, but culture. Ancient calendars followed its cycles. Festivals rose and fell with its phases. Farmers planted by moonlight. Poets found metaphors in its reflection. Lovers and wanderers alike have gazed up and felt seen. In this way, the moon isn't just a rock in orbit. It's a companion, a mirror, a soft light in darkness. Its surface, though lifeless, holds the record of the solar system's early violence. Craters unhealed, dust untouched. Because it lacks weather and plate tectonics, the moon preserves its history in quiet clarity. It is a geological archive, a time capsule drifting above us. A lesser-known discovery came during the Apollo missions. Instruments left on the moon measured lunar quakes, tiny tremors beneath the surface. Some were caused by thermal expansion as sunlight returned after the long lunar night. Others came from tidal stresses as Earth's gravity flexed the moon. Even here, in the quietest of places, motion never fully ceases. And so, the moon circles us, not in perfection, but in steady companionship. It slows us, steadies us, reflects us. We may be the only planet in the solar system with a moon that stabilizes its axis so perfectly that grants us eclipses, that paces our tides like a lullaby. Other planets have moons, yes, but none quite like ours, not in size, not in effect, not in meaning. Astrophysicists still debate whether such moons are common around exoplanets. Perhaps they are, or perhaps the Earth-Moon pair is a rare duet in a mostly silent galaxy. If Earth was designed, the moon may have been part of the blueprint, not merely placed for balance but for beauty, a light for the night, a partner in rhythm, a quiet witness to all that unfolds below. Let's now drift outward, past the glow of our skies and the pull of our moon, into the solar system's quieter edges, where small bodies orbit in near silence. Here, far from the sun's warmth and Earth's familiar pull, we find silent companions, asteroids, Trojans, icy travellers that whisper of ancient beginnings. Though they lack the grandeur of planets or the drama of stars, these objects tell a quieter story, one of preservation, of balance, of things left behind and yet never lost. First, we pass through the asteroid belt, a broad swathe of rocky fragments that lies between Mars and Jupiter. These bodies, ranging from pebble-sized dust to dwarf planets like Ceres, never coalesced into a world of their own. Jupiter's gravity prevented that. Instead, the belt remains a scattered archive, frozen in orbit, holding records from the earliest days of the solar system. One mainstream fact: the asteroid belt contains only a fraction of Earth's mass, spread thin across millions of miles. Despite the cinematic image of ships weaving through crowded rocks, the belt is mostly space. Still, each asteroid is a preserved piece of our solar story, untouched by weather or time. Ceres, the largest, is a round world about 940 kilometers across. It shows signs of ancient water ice and even cryovolcanism, volcanoes that may once have erupted with salty liquid instead of molten rock. A world quiet on the surface but not entirely still. A lesser-known region of balance lies in the Lagrange points, gravitational sweet spots where the pull of two massive bodies, like the Sun and Jupiter, create stable regions. Here, objects can remain suspended, drifting with the planets as they orbit. These regions host the Trojans, asteroids that lead or follow Jupiter in its path around the Sun. The Trojans are curious. There are thousands, and some may be as ancient as the solar system itself. Locked in these stable zones, they orbit in harmony, like dancers holding their distance in a cosmic ballet. They do not collide, they do not stray, they persist. Why do such places exist? They arise from mathematics, the balance of gravitational forces and orbital motion, and yet they feel like quiet corners, safe zones, designed pockets of stillness amid celestial motion. NASA's Lucy mission, launched in 2021, is on its way to visit several of these Trojan asteroids. The goal is to learn more about their composition, their origins. They may hold the secrets to how planets formed, or even why some worlds, like Earth, developed conditions for life, while others did not. Beyond the belt and the Trojans, we reach the Kuiper belt, a distant region filled with icy remnants and dwarf planets. Here, Pluto orbits, along with Eris, Haumea, and Makemake. These worlds are small, cold, and dark. But they too are companions, members of the solar family who orbit far from the hearth, yet remain bound. Pluto, once considered the ninth planet, was reclassified in 2006. Its orbit is eccentric, tilted, and sometimes brings it closer to the Sun than Neptune. Its moon, Charon, is so large relative to Pluto that they orbit a point between them, effectively forming a double dwarf planet. Together they spin in silence, locked in a mutual gaze. Some astronomers believe Pluto and its neighbours are part of a larger population, objects left over from planetary formation. Others propose the existence of Planet 9, a massive unseen world far beyond Neptune, whose gravity may shape the orbits of distant Kuiper belt objects. Its presence is still debated, but its gravitational fingerprint may already be written across the sky. If Earth were designed, perhaps the outer solar system serves as a boundary, a gentle edge, a quiet shelf where time moves slower, light fades, and history sleeps. One curious feature of these outer regions is the cold classical Kuiper belt, a population of the objects with nearly circular orbits, well aligned with the plane of the solar system. Unlike the scattered and tilted orbits of other Kuiper belt objects, these appear undisturbed, as if they've remained in place for billions of years, preserved, protected. Could this be where we store the oldest memories of the Sun? Beyond even the Kuiper belt lies the scattered disk, where objects like Sedna follow elongated, mysterious paths that take them far from the Sun, so far that a single orbit might take 10,000 years or more. These are lonely travellers, barely touched by sunlight, whispering secrets of the solar system's edge. And still farther, we reach the imagined realm of the Oort cloud, a theoretical shell of icy bodies surrounding the solar system at great distance, perhaps halfway to the next star. It has never been directly observed, but its presence is inferred from the paths of long-period comets, those that appear once and then vanish for millennia. If the Oort cloud exists, it may be the solar system's softest shell. A cradle of frozen fragments, a curtain drawn at the edge of sun's reach. Some comets from this region drift inward, their icy tails ignited by sunlight. They sweep through the inner solar system, visible for a few weeks or months, then fade. These visits are reminders of the solar system's depth, of how far it stretches, of how much we have yet to touch. Astrophysicists still debate how these distant populations formed. Were they flung outward by giant planets? Were they captured from other systems during the sun's birth? Are they relics of formation, or messages left by motion? We don't know, but the silence of these regions is not empty. It is full of memory. Perhaps design doesn't always look like construction. Sometimes it looks like preservation, like tucking something away, like creating a quiet place where nothing happens, because nothing needs to. The small companions of our solar system are not loud. They do not shine brightly. They are not crowded with life or wrapped in atmosphere. But they orbit with precision. They persist. They balance. And in their stillness, they offer something rare: time. If Earth was designed, perhaps the outer solar system was shaped as a shelter, a shield, a vault, not just of ice, but of story. From the outskirts of our solar system, let's now shift focus, not to where things are, but to what we can hear, or rather, what we can sense. The universe does not only speak in light, it hums in gravity, pulses in particles, and whispers across vast expanses in signals so faint we barely catch them. If Earth were designed, perhaps some of these signals were meant to reach us, slowly, softly, across time. We begin with the oldest message of all, the cosmic microwave background, or CMB. This faint glow is the afterlight of the Big Bang, light released when the universe was just 380,000 years old. We've mentioned it before, a gentle bath of photons that surrounds us in every direction, stretched by the expansion of space into microwave frequencies. It's a mainstream truth in cosmology. The CMB is a map of the early universe, a frozen image of the moment when light first travelled freely. Its tiny temperature variations, measured to exquisite precision, show us the seeds of galaxies, the blueprints of the cosmic web. In a way, it's not just light, it's memory. A lesser-known aspect of the CMB is its polarization. Light waves from the early universe carry subtle orientation patterns, shaped by the motions and density of primordial plasma. Scientists study these patterns to learn about inflation, the birth of structure, and even gravitational waves from the earliest moments of time. The signal is faint, buried in noise, but it's there, a whisper across deep time. We've built instruments to listen: COBE, WMAP, Planck, each mission mapping the CMB with greater sensitivity. These aren't just observations, they're acts of listening, of tuning ourselves to the language of the cosmos. But not all signals are electromagnetic. Some arrive not as light, but as gravitational waves, ripples in the fabric of space itself. Predicted by Einstein's theory of general relativity, gravitational waves were first detected in 2015 by the LIGO Observatory. These waves came from the collision of two black holes over 1 billion light-years away. The event was violent, but the signal, when it reached Earth, shifted mirrors by less than 1,000th of the width of a proton. It was a quiver in space-time, and we felt it. These detections continue, neutron stars merging, black holes spiraling into darkness, and with each ripple, we learn a little more about the silent dynamics of the universe. A lesser-known effort is underway to detect nanohertz gravitational waves, produced by supermassive black holes orbiting each other across galaxies. These waves are so slow, so vast, that we can't catch them with lasers. Instead, we use pulsars, rapidly spinning neutron stars that emit beams of radio waves like lighthouses. Any change in the timing of these pulses, stretched or compressed, could be evidence of gravitational waves passing between us. This project, known as pulsar timing arrays, transforms the galaxy into a giant observatory. Earth becomes one node among many, listening to the slow undulations of space-time. If design exists, Perhaps it includes signals that arrive only once every 100 million years, too slow for speech, but perfect for patience. And there's more. All around us, at every moment, we are bathed in a ghostly sea of neutrinos, nearly massless particles that rarely interact with anything. Trillions pass through your body every second unnoticed. They come from the sun, from exploding stars, from radioactive decay, from the early universe itself. The cosmic neutrino background, like the CMB, is a relic of the Big Bang. It is even older than light, released when the universe was just 1 second old. We haven't yet detected these primordial neutrinos directly. Their energy is too faint, but physicists are building the tools that may someday reveal them. The quietest particles carrying the earliest whispers. If Earth was designed, maybe these are the background instruments of the great cosmic symphony, so subtle that only the most delicate detectors can hear them. And what of the sounds we ourselves send? Since the early 20th century, we've been broadcasting radio into space, television signals, radar pulses, planetary probes. In all directions, a bubble of human-made noise expands at the speed of light. It has now travelled over 100 light-years, reaching nearby star systems like Vega and Altair. These aren't deliberate messages, just echoes of our activity. But they mark our presence. Some messages have been sent on purpose. The Arecibo message in 1974, a series of binary pulses beamed toward the Hercules constellation. The Voyager golden records, physical disks containing sounds and images from Earth, now drifting in interstellar space. Messages in bottles sent across an ocean we can barely fathom. Astrophysicists still debate whether we should continue sending such signals. Should we speak first, or should we only listen? Might other civilizations be doing the same, waiting, whispering, hoping to be heard? Some wonder why, if intelligent life is common, we haven't heard from it yet. This is the Fermi paradox, the tension between expectation and silence. Perhaps we're alone. Perhaps civilizations rise and fall too quickly, or perhaps the messages are there, but we haven't learned to listen in the right way. A lesser-known speculation is the idea of neutrino communication, the notion that advanced beings might use particles instead of photons, sending messages through the densest regions of space, impossible for us to detect. At least, not yet. If Earth were designed, perhaps the design includes a delay, a waiting period, a quiet time in which to grow, to wonder, before the answers come. For now, we continue to build instruments, we aim antennas at the sky, we cool detectors to near absolute zero, we count photons, track pulses, study echoes, and sometimes we simply sit in the silence. Because even silence is a kind of signal. It tells us where we are. It shapes what we dream. It leaves space for questions. If the universe is a conversation, Earth may be one of its early voices, pausing, listening, and preparing to speak. From signals that hum and fade, we now turn our attention to time itself, not as a ticking clock, but as a vast flowing current. We live not at the centre of the universe nor at its edge, but somewhere in between, in both space and time. And if Earth were designed, perhaps the tempo of time, the way it stretches and curves and flows, was part of that design as well. Time, in our experience, moves forward. We wake, we grow, we age, we remember. The past is fixed, the future unknown. But to physics, time is more flexible, more woven than linear. According to Einstein, time is not a separate stage on which events unfold. It is part of the stage itself. It curves with gravity. It stretches with motion. This brings us to a mainstream truth. Time runs differently depending on where you are and how fast you move. Near massive bodies like Earth, time flows slightly slower. This effect, called gravitational time dilation, has been measured with incredible precision. so precise in fact that your feet experience time just a little slower than your head, simply due to gravity's gradient. If Earth were designed, maybe this subtlety was included not to be noticed daily, but to reveal itself as understanding deepened. A small clue, a quiet nod. But there is a larger mystery. Why does time flow at all? Most fundamental equations in physics are time-symmetric. They work forward or backward, and yet we experience time as directional, as an arrow moving from less to more disorder, from low entropy to high. Entropy is a measure of randomness, of possibility. The universe began in a state of extremely low entropy, highly ordered. Since then, it has been relaxing, spreading, softening. Stars form, burn, and fade. Heat moves from hot to cold. Order dissolves into mixture. This direction, the arrow of time, may be a consequence of entropy itself. But the reason why the universe began in such a low entropy state is still unknown. Was it necessary? Or was it a choice? Some speculate that the early universe had to be smooth and simple to allow structure to form later. Others wonder whether our view of entropy is incomplete, that perhaps in a deeper framework, time and order are illusions shaped by our limited perspective. A lesser-known idea is Janus time, a hypothesis that suggests the universe may have two time arrows, flowing in opposite directions away from a shared low-entropy origin. If true, there could be another branch of the universe, expanding in the opposite temporal direction. A mirror world where time flows backward, at least from our perspective. Could such a structure exist not as accident, but as symmetry? Earth, in this context, becomes not just a planet, but a moment. A pause along a slow tide. Our lives are brief pulses in a timeline billions of years long. And yet, we are made of things older than Earth itself. The atoms in our bodies were forged in stars that lived and died before the sun was born. Some of the hydrogen in your water is nearly as old as the universe, and time affects not only us, but how we see. Light takes time to travel. When we look at distant galaxies, we see them not as they are now, but as they were millions or billions of years ago. The deeper we peer, the further back in time we reach. The observable universe is like a memory, finite, glowing, fading as we gaze toward its limits. This leads us to the concept of the cosmic horizon, the boundary beyond which light hasn't had enough time to reach us since the beginning of the universe. It isn't an edge, but a limit. Beyond it, galaxies may exist, but their light lies forever out of reach. We will never see them, never know them. They are part of the universe, but not part of our story. That horizon is not fixed. As time passes, it expands. More of the universe becomes visible, but at the same time, cosmic acceleration, driven by dark energy, is pulling distant galaxies away faster and faster. Eventually, most of the sky will darken. The stars we see today will fade from view, red shifting into invisibility. A lesser-known projection from astrophysicists is that, in 100 billion years, even nearby galaxies may lie beyond our ability to detect. Future civilizations, if any remain, might see only their local group. The universe will seem empty, the cosmic story erased by distance. If Earth were designed, perhaps this fading horizon was part of the structure, a kind of veil, a way to encourage wonder before the curtain closes, or perhaps it's only a natural consequence of space expanding into silence. The flow of time also plays a role in planetary habitability. Life needs not just a place to emerge, but time to unfold. Stars must burn steadily. Climates must remain within certain ranges. Evolution takes billions of years. Too fast a pace, and life is crushed. Too slow, and complexity may never arise. Earth orbits a star whose main sequence lifespan is around 10 billion years, long enough, perhaps, for minds to form and reflect. Design, if it exists, may not lie in events, but in timing. Our moon's distance from Earth is increasing, slowly. Each year it moves away by a few centimetres. One day it will drift too far to create total eclipses. The age of perfect solar eclipses is temporary, a celestial coincidence of time and size. We live during the brief era when sun and moon share the sky in just the right proportions. Future skies will change. Was this window of wonder opened deliberately? Even the stars themselves have lifetimes. The sun will one day swell into a red giant, consuming Mercury, perhaps Venus, and bathing Earth in searing light. Eventually, it will collapse into a white dwarf, fading over trillions of years. Other stars will follow. The universe will cool. Black holes will evaporate. In time, all structure may fade. Time, it seems, does not preserve. It transforms. And yet, here we are, in a moment where the sky is full of stars, where light still reaches us from billions of years ago, where matter is still warm and Earth is still gentle. Astrophysicists still debate whether time is fundamental or emergent, whether it is built into the fabric of space, or whether it arises only in certain conditions like temperature or gravity. Some wonder if time exists at all, or if it is merely the way we organize experience. In the soft quiet of the question, we find ourselves returned to the rhythm of breath, the slow cycles of days and nights, the turning of seasons, the long patient drift from birth to age. If Earth were designed, perhaps time itself was the first gesture, a slow unfolding, a pause between silences, a place where motion could become meaning. We've drifted through stars and shadows, through signals and time, and now we find ourselves turning gently toward the question that lies at the heart of it all: life. Not as a spark, not as a moment, but as a possibility woven into the fabric of the cosmos. If Earth was designed, then perhaps life itself was part of that design. Not inevitable, perhaps, but quietly permitted, gently encouraged. Life, in our experience, is fragile. It needs warmth, water, protection from radiation, a stable surface, a chemistry rich in carbon and oxygen. But the universe is not empty of these things. The basic ingredients of life, hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, are among the most common elements in the galaxy. One mainstream truth: carbon-based molecules form with remarkable ease in space. In the dense clouds between stars called interstellar molecular clouds, astronomers have detected complex organic compounds, amino acids, alcohols, even simple sugars. These molecules form in the cold and dark, clinging to dust grains, drifting for millions of years. Some fall into new star systems, some are caught in comets, some perhaps find their way to young planets. This discovery reshapes our view of life's origins. It may not require a miraculous beginning, just time, warmth, and chemistry. Earth might not have created life from scratch, but inherited the building blocks from the stars. In this way, life begins long before cells. It begins with starlight and dust. A lesser-known observation involves meteorites like the Murchison meteorite, which fell in Australia in 1969. Inside were over 70 amino acids, many not found on Earth. These were not contaminants. They were formed in space, preserved in rock, and delivered across time. A reminder that life's chemistry is not confined to Earth. It is written across the cosmos. Astrobiologists still debate whether life on Earth arose independently, or whether it was seeded, not in the directed sense of delivered, but through a process called panspermia, where microbes or organic molecules travel between worlds on comets or meteorites. It's speculative, yes, but it suggests that Earth may not be alone in its capacity for life. Could life be common? Could it emerge wherever conditions are right? To explore this, we often look to exoplanets, worlds beyond our solar system. Thousands have been discovered, many in their stars' habitable zones, where temperatures may allow for liquid water. Some orbit stars similar to our Sun. Others circle dimmer red dwarfs with tight, fast orbits and tidal locking. These planets are varied, strange and beautiful. Some are larger than Earth, rocky and blue. Others are icy, distant, shrouded in methane. Some may host clouds of sulfuric acid. Others may hide oceans beneath crusts of ice. Their diversity reminds us that Earth is not the only possible configuration. Life may adapt in ways we can't yet imagine. A lesser-known category is the super-Earth, a planet larger than Earth but smaller than Neptune. These worlds may have thicker atmospheres, stronger gravity, and more persistent tectonics. Some models suggest they could be more stable over time, offering even better conditions for life. Could such a world somewhere far away host oceans and forests of its own? And yet, we haven't found a twin. Not exactly. Earth is the only known world to host life. Despite all our searching, we have yet to hear a voice in the silence. No signals, no artifacts, no undeniable biosignatures. This absence deepens the mystery. It sharpens the question. Is life rare, or is it simply quiet? We might pause here to reflect on biosignatures, chemical clues that life may be present. Oxygen in large quantities, for instance, is unlikely to accumulate without photosynthesis. Methane, too, can indicate biological activity. Telescopes like the James Webb are now scanning the atmospheres of distant planets, looking for these signs. But detecting a biosignature is not confirmation. Oxygen can arise through non-living processes, so can methane. The search continues, the silence deepens, and in the meantime, we look closer to home. Earth is not the only world with water. Europa, one of Jupiter's moons, harbours a global ocean beneath a crust of ice. So does Enceladus, orbiting Saturn, which sprays water vapour and organic molecules into space through geysers near its south pole. These subsurface oceans are kept warm by tidal forces, gravitational flexing that generates heat. They are dark, but not still. Is it possible that life stirs there in the deep? We do not know, but if Earth was designed, perhaps it was not designed alone. Perhaps there are other worlds where life flows, not as a mirror of ours, but in wholly different rhythms. Perhaps there are forms of awareness so alien we would not recognize them, not because they are hidden, but because we are unprepared to see. And yet one cannot help but wonder whether Earth was made not only to host life, but to nurture consciousness. Not merely biology, but thought, the ability to notice the stars, to ask questions, to reflect. This is where the design, if it exists, becomes personal. For life to emerge is one thing, for it to look up and wonder, that is something else entirely. One lesser-known feature of life on Earth is chirality, the handedness of molecules. Biological amino acids all share the same left-handed orientation. This asymmetry is universal in Earth biology, but has no known reason. In lab conditions, both hands form. In nature, only one dominates. Was this a frozen accident, or a subtle preference locked into life from the start? The implications are deep. If we found right-handed life elsewhere, it might suggest an independent origin. If we found left-handed life, it could suggest a shared ancestry. The details are small, but the meaning might be vast, and so we carry the question gently. Is life a miracle or a pattern? Was Earth chosen or fortunate? We do not have answers, but the pieces, the carbon clouds, the icy moons, the drifting amino acids are out there, like scattered notes in a melody only partly written. If Earth was designed, life may not be its purpose, but life, in all its quiet resilience, might be the outcome, the flowering of form, the breath between atoms. The slow awakening of awareness, a pause, a heartbeat, a gaze turned toward the stars. As we float farther into the vastness, our gentle wandering begins to turn outward, to possibility, to others. If Earth was designed, we might ask next, were others designed too? Are we alone in this hush, or are there other minds, breathing quietly beneath alien skies, also gazing upward, also wondering? The search for intelligent life, not just microbes or molecules, but beings who think, build, dream, is one of the most profound quests in astronomy. We call this field SETI, the search for extraterrestrial intelligence. And though it is scientific, it also feels personal, poetic, and deeply human, because to search is to hope. One mainstream fact is that SETI involves scanning the sky for narrowband radio signals, signals that are not easily produced by natural processes. Such signals could, in theory, be broadcast by a civilization trying to communicate across the stars. For decades, radio telescopes have listened, sweeping across the sky like giant ears, and so far, nothing. No confirmed signals, no unambiguous signs, just the quiet crackle of background noise, the occasional spike, the long hours of silence. This silence has a name, the Fermi paradox. It asks a simple, haunting question. If the universe is so vast, so old, and filled with billions of stars and planets, then where is everyone? There are many proposed answers. Perhaps intelligent life is exceedingly rare. Perhaps it tends to destroy itself before it can reach the stars. Perhaps civilizations simply don't want to communicate, or perhaps they do, but they speak in ways we don't understand, or on timescales we cannot yet follow. A lesser-known suggestion is the idea of a zoo hypothesis, that advanced civilizations might be aware of us, but deliberately avoid contact, allowing us to evolve naturally without interference, like placing a veil between worlds until we're ready. If Earth was designed, this idea might take on new weight. What if we're meant to reach out first or only after we've grown? Others speculate about the Great Filter, a barrier in the evolution of a life that is extremely hard to pass. If it lies behind us, then we may be rare survivors. If it lies ahead, then perhaps our moment of quiet balance is more fragile than we know. Still, we keep listening, and sometimes we speak. In 1977, the Voyager spacecraft were launched. On board were golden records, metal discs engraved with sounds and images of Earth, greetings in dozens of languages, music from across cultures, diagrams of our solar system, and even a child's laughter. These messages were not practical communications. They were symbols, artifacts meant to say, we were here, we noticed. Voyager 1 has now entered interstellar space, the first human-made object to do so. It drifts farther each day, its signal growing fainter. Long after Earth is gone, the golden record may continue, spinning silently, carrying fragments of who we were. If Earth was designed, perhaps the ability to wonder about others was part of the design. Not just the drive to survive, but the urge to connect, to reach. A lesser-known project underway today is Breakthrough Listen, a major scientific initiative to scan 1 million stars for signs of intelligent life, using some of the world's largest telescopes. It analyzes petabytes of data, searching for patterns that deviate from nature's randomness. Even if no signal is found, the effort itself is profound. It marks a species willing to look up and to wait. And what if the signal never comes? Would that make us alone? Or would it make us first? Perhaps Earth is not one of many similar worlds, but one of the early ones. Perhaps the galaxy is still waking up. Stars like our Sun live for billions of years. Civilizations may be rare but long-lived. Maybe the galaxy will bloom slowly, mind by mind, until the sky's filled with voices. We may be at the dawn, not the twilight. It's also possible that life arises, but intelligence is rare. Or that intelligence does not always lead to technology. Some creatures may be sentient, even wise, but remain bound to their homeworlds. Others may choose silence, finding contentment in their own skies, uninterested in reaching out. Intelligence does not always build radio towers, and even if others are out there, distance remains a challenge. The nearest star system, Alpha Centauri, is over 4 light-years away. A signal would take years to travel there, and even longer to return. And that's still in our neighbourhood. Most stars are far more distant. Communication, if it happens, would be glacial. Not conversation, but correspondence. Not answers, but echoes. Still, we imagine. We write stories of galactic meetings, of ancient civilizations, of wisdom shared across light years. These are not predictions, they are longings. They remind us that we are a species that looks beyond the horizon, even when there is no path, even when the stars are silent. Some wonder whether the design, if it exists, might not be in the presence of others, but in their absence. Perhaps Earth was made to be alone, at least for a time, to grow without influence, to learn without guidance, to ask questions before answers arrive. There is also the possibility that the signs are already here, but misinterpreted. Perhaps intelligent life leaves behind subtle changes in a planet's atmosphere, or shifts in energy patterns or constellations reshaped by engineering we cannot yet detect. Maybe we need new instruments, or new ways of seeing. A lesser-known idea is Dysonian SETI, the search for megastructures or energy signatures, rather than direct communication. Could alien civilizations harness stars, build swarms of satellites, or create artificial pulses of light? One famous case involved a star, Tabby star, that dimmed irregularly in ways that puzzled scientists. Some speculated about alien technology. Most likely it was dust, but the fact that we asked the question, that we dared to consider it, says something. If Earth was designed, perhaps part of that design is the waiting, the readiness, the capacity to hope, and perhaps in this vast silence, we are being taught to listen more deeply, not just for others, but for ourselves. For now, we continue to scan the skies. We refine our instruments, we decode signals, we write messages for futures we may never see. And as we wait, the stars remain, distant, bright, watching. If Earth is not alone, then one day perhaps the silence will break, and we will look up, not into the void, but into a voice. Let's now shift our gaze once again, from distant minds to the invisible framework around us. Not the stars, not the galaxies, not even the space between them, but the substance that seems to shape it all without ever showing its face. If Earth were designed, perhaps it rests on a scaffold we cannot see, held together by something mysterious, silent, and strangely essential. We call it dark matter. This is a mainstream truth in modern cosmology. Galaxies rotate too quickly for their visible mass alone to hold them together. Stars on the outskirts spin as fast as those near the centre, when, by all rights, they should be flung into space. Something must be adding gravity, something we do not see, do not touch, do not even interact with, except through its pull, and so we infer the presence of a hidden mass, dark matter. It does not emit light, absorb light, or reflect it. It passes through ordinary matter like wind through a screen, and yet it shapes galaxies. It forms the framework of galaxy clusters. It bends light through gravitational lensing. It whispers in gravity, not in glow. The idea may seem strange, but the evidence is vast. Models of cosmic structure formation, how galaxies and filaments emerged from the early universe, only work if dark matter is included. Without it, the structures we see would never have had time to form. It is the unseen bones of the cosmos. If Earth was designed, then dark matter might be the invisible lattice upon which that design was built, and yet we do not know what it is. A lesser-known possibility is that dark matter could consist of axions, hypothetical particles so light they might behave more like waves than particles. Another candidate is WIMPs, weakly interacting massive particles that might occasionally collide with normal matter, though we've yet to confirm such an event. Experiments like Xenon, Lux Zeppelin, and Dama Libra sit deep underground, shielded from cosmic rays, watching for the faintest signs of dark matter's passage. So far, the results remain elusive. No confirmed detection, only the suspicion of something present just beyond our reach. Could it be that we're not meant to detect it, only to feel its influence? That the universe holds some truths not in visibility, but in effect? If dark matter forms halos around galaxies, then Earth itself resides within one, a vast cloud of invisible mass wrapping the Milky Way. We move through it daily, unaware. It does not press upon us. It does not burn or hum. It only holds. And yet, this is only half the puzzle. The other half is even more mysterious. We call it dark energy. In the late 1990s, astronomers discovered something unexpected. The expansion of the universe is not slowing down. It's speeding up. Galaxies are not merely drifting apart. They're accelerating away from one another, driven by some unknown pressure in space itself. This pressure, whatever it is, makes up roughly 68% of the total energy content of the universe. Dark matter is about 27%. That leaves ordinary matter, everything we see, touch, measure, as just 5%. Let that settle for a moment. Everything, stars, planets, people, oceans, light, is a small fraction of what the universe contains. The rest is hidden, silent, acting behind the curtain. Some liken this to discovering that the book we've been reading is only the outer layer of a much deeper story, that the part we can read is just the binding. If Earth was designed, perhaps the true shape of that design lies in what we can't yet see, in the subtle guidance of expansion, in the tension between gravity and growth. A lesser-known aspect of dark energy is the possibility that it isn't a constant. Some models suggest it could vary over time, a field rather than a fixed value. This hypothetical field is sometimes called quintessence, a term borrowed from ancient philosophy, where it referred to the fifth element, the pure essence of heaven. It's a poetic name for a concept so subtle we're not sure it's even real. Astrophysicists still debate the nature of these forces. Is dark energy truly energy, or is it a property of space? Could it arise from quantum fluctuations? Could it be a sign that our understanding of gravity needs to change? Perhaps. Or perhaps it is something else entirely. There is also a question of fate. If dark energy continues to accelerate the expansion, the universe may drift into a cold, dark future, a so-called heat death, where stars fade, black holes evaporate, and even atoms dissolve. No collapse, no fire, only the long sigh of space stretching into silence. Alternatively, if dark energy strengthens over time, the cosmos could face a big rip, where galaxies, stars, planets, even atoms are torn apart by expansion itself. A quiet unravelling, and yet it may also level off. It may balance. It may create room for other possibilities we have yet to imagine. Some speculative models even suggest that dark energy and dark matter might be linked, that they arise from the same hidden layer of reality. If so, we may be glimpsing not just forces but architecture, the quiet machinery of the cosmos. If Earth was designed, then perhaps it was placed not within the light, but within the tension, between gravity and flight, between the visible and the hidden, because design does not always reveal itself in surfaces. Sometimes it lives in scaffolding, in silence, in the unseen shapes that hold everything steady. We orbit within a galaxy shaped by invisible mass. We drift outward on the tide of dark energy. We are the 5% carried by forces we do not yet understand. And yet, here we are, breathing, wondering, building instruments to listen. There is something beautiful in not knowing, something soft in the pursuit. The mystery itself becomes part of the rhythm. And even if we never uncover the full truth, the search lets us dwell in the quiet between questions. If there is a design, perhaps it's not in answers but in this openness, a frame wide enough to include silence, doubt and awe. Having drifted through the scaffolding of dark matter and the quiet push of dark energy, we return now to something more intimate: chemistry. Not as a branch of science, but as a whispering thread, a quiet story written in the language of atoms. If Earth was designed, perhaps the chemistry of life, the recipes for breath and blood, stone and sky, was part of the blueprint. Let us begin with carbon. It is in many ways the backbone of biology. One mainstream truth is that carbon atoms can form 4 stable bonds, a simple property that enables complex molecules to arise. It can create long chains, branching structures and rings. It bonds flexibly with hydrogen, oxygen, nitrogen, sulfur and phosphorus. In doing so, it becomes the scaffolding for proteins, nucleic acids, lipids, and sugars. The versatility of carbon may seem inevitable, but it is in fact remarkable. It is stable, but not inert. Reactive, but not volatile. It occupies a sweet spot in the periodic table, a place that allows both structure and flexibility. No other element quite replicates this balance. If Earth was designed, carbon's properties could be viewed as a kind of quiet permission, an open gate through which life might pass. A lesser-known detail is the abundance of carbon chains and rings found in interstellar space. Using radio telescopes, astronomers have detected polycyclic aromatic hydrocarbons, cyanopolines, and other complex molecules drifting between stars. These are not signs of life, but they are hints of potential, building blocks scattered widely. Perhaps the universe is not sterile, but preloaded. Not in a literal manufactured sense, but in a soft way, as though the ingredients were seeded with care. We might also consider water, again, this time not just as a solvent, but as a medium for chemical reaction. Water allows molecules to dissolve, move, collide, react. Its polarity enables the formation of membranes. Its high heat capacity moderates temperature. Its transparency lets light through. These are not just conveniences, they are enablers. A lesser-known property of water is its density maximum at 4 kTx. As water cools, it becomes denser, until just before freezing, when it begins to expand. This keeps the bottom of lakes from freezing solid, preserving aquatic life through winter. Such a small anomaly, such a quiet safeguard. And then there is oxygen. We think of it as the breath of life, but it was once a poison. Early Earth had little free oxygen. Life began in anaerobic environments, using other molecules to transfer energy. Only later, with the rise of photosynthetic microbes, did oxygen begin to accumulate. The Great Oxygenation Event, around 2.4 billion years ago, transformed the atmosphere and almost caused extinction. But from this disruption came opportunity. Oxygen enables far more efficient metabolism. It made multicellular life possible. It made complexity possible. A lesser-known aspect of oxygen is its role in creating the ozone layer. High in the atmosphere, oxygen molecules absorb ultraviolet radiation and split into atoms. These atoms recombine into ozone, which blocks harmful UV from reaching the surface. Without it, land-based life might never have emerged. If Earth were designed, perhaps it was designed not only for life to emerge, but for life to adapt, to shift, to risk. Because the chemistry of life is not gentle. It is explosive, reactive, unstable. But within that chaos, patterns emerge. Cycles take shape. Take, for example, the carbon cycle, a planetary rhythm that moves carbon between air, ocean, rock, and life. Volcanic eruptions release carbon dioxide. Plants absorb it. Animals exhale it. When organisms die, carbon returns to soil. Some is buried, becoming coal, oil, or limestone. Over time, tectonic forces return it to the surface. This is not design in the architectural sense, but it is system, it is connection. The nitrogen cycle offers another quiet loop. Though nitrogen makes up most of Earth's atmosphere, it is largely inaccessible to life in its gaseous form. Certain microbes fix nitrogen, converting it into forms plants can absorb. Animals eat plants, waste returns nitrogen to the soil. Lightning and fire also play a role, a dance of conversion powered by storms and roots. A lesser-known feature here is the role of symbiotic bacteria, microbes that live in the root nodules of legumes, fixing nitrogen in exchange for sugars, a partnership written in molecular terms. If Earth was designed, perhaps it was not as a finished product, but as a living canvas, painted not once, but endlessly. We should also reflect on phosphorus, an essential element for DNA, cell membranes, and energy transfer. Unlike carbon or nitrogen, phosphorus is scarce and tends to bind tightly with other minerals, limiting its availability. Some scientists believe phosphorus availability may be a bottleneck for life elsewhere. Its distribution on Earth may not be typical. A lesser-known question is how phosphorus became bioavailable. Some suggest it arrived in reactive form via meteorites, especially from a mineral called schreibersite, found in iron-rich meteorites. This would mean that life's emergence depended not just on Earth's chemistry, but on the chemistry of impact. And so, even collisions become part of the story. These building blocks, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, form the acronym SHNOPS. They are found everywhere, yet they organize themselves only in very specific ways, in spiral DNA, in folded proteins, in lipid bilayers, structures that self-assemble, guided by shape and charge. If Earth was designed, perhaps the design is not in the components, but in the rules of assembly, not in the puzzle pieces, but in the laws that tell them how to fit. We often picture design as something with intent, with a finished goal. But what if the design of Earth was more like the design of a language? Not a sentence written out, but an alphabet, a syntax, a set of relationships that allows new meaning to emerge again and again. Chemical design is not rigid, it is potential, it is capacity, and in that capacity Earth excels. Its oceans are not just water, they are solutions. Its rocks are not just stone, they are batteries. Its air is not just wind, it is mixture and motion. Every element of Earth participates in a larger pattern. Nothing stands alone. Even calcium, the element in our bones, arises from dying stars. Even iron, which carries oxygen in our blood, was forged in supernovae. We are made of process, of fusion and decay, of fire and molecule. And yet, here we are, shaped by forces that do not know our names but that nonetheless gave us form. If Earth was designed, perhaps the most remarkable part is not that life exists, but that chemistry keeps making it possible. Having explored the subtle balances of Earth's chemistry, we now rise to a broader and more open question, perhaps the most tantalizing of all. Is Earth unique? Is this world, with its oceans, air and awareness, a rare gem in a quiet universe, or one of many, part of a common design echoed across the stars? This is the tension between two ideas. The rare Earth hypothesis, which suggests Earth is an extraordinary exception, and the principle of mediocrity, which argues that our planet is unremarkable, typical even, and that life like ours might be widespread. Both views are humbling. One says we are astonishingly rare. The other says we're part of something vast. One mainstream truth is that exoplanet surveys have found thousands of planets orbiting other stars, some small, some large, some rocky, some wrapped in gas. Many stars host multiple planets, and a growing number of these planets lie within the so-called habitable zone, where liquid water could exist. Statistically, Earth-like planets may number in the billions across our galaxy alone. But Earth-like is not simple. It doesn't just mean rocky and not too hot. It also implies atmosphere, magnetic field, stable orbit, geological activity, surface water, and long-term climate stability. When all these factors are considered together, the field narrows, and it becomes harder to say how common another Earth really is. The rare Earth hypothesis, introduced by Peter Ward and Donald Brownlee, argues that life is fragile, that it depends on a long series of unlikely events, a large stabilizing moon, protective gas giants nearby, plate tectonics, a galactic neighborhood free from too many supernovae. The argument is not that planets are rare, but that life-supporting conditions are rare, especially for complex life. A lesser-known factor in this discussion is Earth's position in the galactic habitable zone, a region not too close to the centre of the Milky Way, where radiation and gravitational disturbances are high and not too far out, where heavy elements become scarce. Earth lies in a middle band, where stellar metallicity and relative calm allow life to flourish. Was this placement accidental, or was it part of the positioning? Another element to consider is time. Earth is about 4.5 billion years old. The universe is more than 13 billion years old. That means there were planets forming billions of years before Earth even existed. If intelligent life is common, we might expect civilizations far older than ours. So why don't we see their traces? This loops us once again back to the Fermi paradox. Some suggest that life is common, but intelligence is not. Or that intelligence emerges, but rarely becomes technological. Or that civilizations collapse before they can spread. Others point to the Great Silence, the absence of alien artifacts, megastructures, or unexplainable engineering feats. If Earth were one of many designed worlds, shouldn't we see signs of others? But perhaps the design is quiet by intention. Perhaps each world is given space, room to grow, to reach, to listen. It's possible that life tends to stay close to home, that biology is bound not just by physics, but by temperament. Maybe some civilizations don't seek expansion, or maybe they go inward, into digital realms, into silence. We often imagine the galaxy full of signals, lights, structures, but perhaps it is full of restraint. Perhaps Earth's quietness is not loneliness, but etiquette. A lesser-known idea called the estivation hypothesis suggests that advanced civilizations may go dormant, choosing to wait until the universe cools, when computation becomes more efficient. They would be silent not because they're absent, but because they are patient. If true, it would mean the galaxy is full and sleeping. And yet, Earth feels singular, not just in its physics, but in its invitation. We live on a planet that seems just right in too many ways to count. The length of our day, the mix of gases in our air, the gravity strong enough to hold oceans but gentle enough to allow birds to fly, the transparency of the atmosphere, letting in sunlight but blocking most harmful rays, the rhythm of tides, the thickness of our crust, the placement of iron at our core, the coincidence of eclipses, the deep thermal energy beneath our feet, the layering of habitats, sky, mountain, forest, river, ocean trench. Each condition seems independent, but together they sing in harmony. Is that harmony unique? Astrobiologists still search for biosignatures, chemical hints of life, in the atmospheres of distant worlds, and the search is only beginning. Within a few decades, we may know if Earth's uniqueness is an illusion born of ignorance, or a truth that must be honoured. A lesser-known detail, the Kepler 442b exoplanet, about 200 light-years away, is rocky, Earth-sized, and within its star's habitable zone. It receives roughly 2/3 the sunlight of Earth, and may have a more stable orbit. In some simulations, it might even be more habitable than Earth, and yet we don't know if it has air, or oceans, or life. Perhaps it does. Perhaps billions of worlds do. But until we hear a voice, or catch a shadow, or see a flicker, we are left with our own. And maybe that's the point. If Earth was designed, maybe it was not as a copy in a series, but as a seed, a starting point, a singular experiment in consciousness, or perhaps one thread in a larger design, scattered, hidden, gentle. We don't know yet if we are rare, but we do know we are here, and we know that this world, with its green flash at sunset and its sound of rain on leaves, is worth caring for, whether it's one of many or the only one. The universe has given us Earth, at least for now, and maybe, whether by chance or by care, that is risen enough to listen, to watch, to wonder, to treat it not as common, but as precious. Let's linger now on the quietest part of the question, not just whether life exists elsewhere or whether Earth is unique, but whether someone is watching. Not in the celestial mythic sense, but in the soft, scientific wondering. Could intelligence, somewhere out there, be aware of us? If Earth was designed, then perhaps it was designed not only to harbour life, but to be observed. Perhaps, just perhaps, we are not just the watchers, but the watched. We've considered SETI, exoplanets, the Great Silence. But there is another layer to this mystery, one filled with strange absences, unlikely coincidences, and deep restraint. It's not just that we don't see anyone, it's that we don't see any footprints. The universe is over 13 billion years old. If any civilization had emerged millions or billions of years before us and developed even modestly advanced technology, they might have spread, colonized, reached across stars, left traces, satellites, signals, structures, and yet we see no Dyson spheres, no city-sized machines, no star system rearrangements. The galaxies remain as they were, stars still burn naturally, planets spin quietly. If intelligence is out there, it has left almost no mark. One mainstream proposal is the rare intelligence hypothesis, the idea that while microbial life may be common, technological intelligence is vanishingly rare. It may require too many steps, too many layers of luck. Earth, in this view, is not just rare, it is a singularity of mind. A lesser-known variation is the silent watchers concept, suggesting that other intelligences may have a different approach altogether. Perhaps they observe quietly, never interfere. Like cosmic anthropologists, they watch our species evolve, speak, dream. Not because they are absent, but because they are patient. It sounds like fiction, but even in science, this thought emerges in unexpected places. Philosophers and physicists have proposed simulation hypotheses, zoo models, and even information-based cosmologies in which the fabric of reality is itself a kind of processing system, sensitive to observation, responsive to inquiry. These are speculative, yes, but they arise naturally from our deep desire to be known, to not be alone. And perhaps this feeling isn't just emotional. Perhaps it reflects something deeper. The universe, after all, does seem to respond to observation in strange ways. At the quantum level, measurement affects outcome. Particles behave differently when watched. Is this mere math, or a window into something we don't yet understand? A lesser-known fact is the idea of the participatory anthropic principle, the idea that observers play a role in shaping reality, not just seeing the universe, but helping to define it. That without awareness, the cosmos remains incomplete. It's not a mainstream belief, but it's not easily dismissed either. If Earth were designed, maybe it wasn't built as a closed system. Maybe it's part of a network, a garden in a gallery, one bloom among many, and we are only just learning to open our eyes. SETI has often asked whether we should transmit as well as listen. Should we announce our presence or remain quiet, waiting? The question divides scientists. Some fear alerting the wrong kind of listener. Others believe we've already spoken, our signals, our lights, our probes, all drifting outward, carrying evidence of thought. And then there is the question of first contact. Would it come as a message, a visit, a pattern in the sky, or would it come as an insight? A quiet shift in understanding, triggered not by evidence but by readiness. Perhaps intelligence elsewhere is not watching us directly, but watching the conditions for life, for awareness. Maybe Earth is part of an experiment, a test bed. Or perhaps a story unfolding slowly, naturally under the long gaze of distant eyes. A gentler idea is that there are no watchers at all, at least not in the sense we imagine. That we are for now alone with our questions. That the silence isn't ominous but spacious. It gives us room to grow, to choose who we become without influence, to be our own guides. Even in that version, the possibility of being watched by future minds, by memories not yet formed, still hovers. Perhaps what matters isn't whether someone is watching. Perhaps what matters is that we act as if someone were. This is the essence of stewardship, of legacy, of care. If Earth were designed, perhaps part of that design is this very impulse to protect, to wonder, to reflect, to be accountable, even when no one is looking. We might think of it this way. Even if we are alone, we still carry the responsibility of being the only known intelligence. We are, in this moment, the universe's only confirmed mirror, the only place where atoms have arranged themselves into a being that can say, "I see." That is not arrogance, that is humility. It is the humility of the candle that knows its own flame, and so we walk gently. We study, we ask, we build. We send telescopes to orbit, we launch probes into the dark. We scan the sky for pulses of light, patterns of timing, whispers of intention. We teach our machines to listen harder, to scan deeper. We collect data not because we expect an answer, but because asking the question matters. A lesser-known SETI experiment involved modulated laser pulses aimed at nearby stars. The idea, perhaps other civilizations watch in optical wavelengths, not radio. Or perhaps they speak in mathematics, not language. In ratios, not sentences. In patterns, not voices. If Earth was designed, perhaps it was designed to wake up slowly, to reach awareness in stages, to not be overwhelmed, to grow into its own gaze. And perhaps one day we will find something, or perhaps we won't. But either way, the act of watching, of wondering, is part of the design itself. Because even without watchers, even without messages, we see. And in that act, Earth becomes not just a world, but a witness. We now turn inward once more, towards something even more mysterious than dark matter or intelligent watchers, toward the unseen forces that shape the universe at every level, but remain profoundly unknown. If Earth was designed, then perhaps the design includes unfinished scaffolding, structures half hidden, half understood, shapes traced in gravitational pull and quantum flutter. Among these we find two of the greatest enigmas, the nature of reality's hidden geometry and the limits of what can be known. We've already whispered about dark matter and dark energy, the unseen majority. But we've yet to consider the framework that holds everything together, not just across space, but across possibility. Let's begin with the shape of the universe. A mainstream truth: space can curve. Einstein showed us that mass tells space how to bend, and bent space tells mass how to move. On cosmic scales, this curvature matters. It affects how light travels, how galaxies form, and how the universe expands. Observations suggest our universe is spatially flat, meaning that, on average, parallel lines never meet, and triangles add up to 180 degrees. But this flatness may be local, an illusion created by a much more complex global geometry. A lesser-known possibility is that the universe could be finite but unbounded, like the surface of a sphere but in 3 dimensions. In such a universe, you could travel in a straight line and eventually return to your starting point, never encountering an edge. The space would curve back on itself, endless yet enclosed. If Earth were designed, perhaps it was placed in just such a realm, a universe without edges, without centers, where the journey is circular, not linear, a soft constraint, a geometry built for wandering. Another mystery lies in the constants of nature: the speed of light, the gravitational constant, Planck's constant, the mass of the electron. These values shape every atom, every star, every breath. Change any one slightly, and the universe as we know it collapses. No stars, no chemistry, no life. This delicate balance has led some to propose the fine-tuning problem, the observation that the physical constants appear to be just right for life. If gravity were slightly stronger, stars would burn too quickly. If electromagnetism were weaker, atoms might not hold together. The odds of hitting the right combination seem astronomically low. Some physicists answer this with the multiverse hypothesis, the idea that our universe is one of many, each with different constants. Most would be barren. Ours is simply one where life can arise. We're here to observe it because we can be here. But others suggest this precision is too striking to ignore, that perhaps the values were selected, not randomly, but quietly. If Earth was designed, perhaps the fine-tuning of physics is part of the design itself. Not flashy, not overt, just exact. A lesser-known detail is that some constants may not be constant. There's speculation, still debated, that the fine structure constant, which governs the strength of electromagnetic interaction, may have varied slightly over cosmic time. If so, that raises profound questions. Is the universe still being tuned? Is the scaffolding still being adjusted? That leads us into even deeper waters, the holographic principle. This is not science fiction. It's a serious theoretical idea in modern physics. It suggests that everything we observe in three-dimensional space, including you, me, Earth, galaxies, might be described by information encoded on a distant two-dimensional boundary. In this view, the universe is not made of particles, but of information. A kind of cosmic data structure. Space and time merge from this deeper layer, like a 3D image unfolding from a flat screen. This principle arises from black hole physics. When matter falls into a black hole, its information seems lost. But that leads to paradoxes. To resolve them, physicists discovered that the surface area of a black hole, not its volume, contains the information of what's inside. If Earth was designed, perhaps that design exists not in space, but in encoding, in patterns that underlie what we perceive, a quiet script not in symbols, but in states. We don't yet know if the universe is holographic, but experiments are being imagined to test it. If true, it would mean that what we call physical reality is emergent, not fundamental. And what then is real? Quantum physics already tells us that particles don't have fixed positions until measured. That superposition, being in many states at once, is real. That entangled particles can affect each other instantly across vast distances. That uncertainty is not a bug, but a feature. A lesser-known idea in this space is quantum decoherence, the process by which a quantum system becomes classical, losing its ambiguity through interaction with the environment. It's how a particle's wave-like nature chooses a state when observed, and it suggests that reality is not absolute, it is contextual. Could the entire universe be a kind of unfolding observation? Some thinkers go further. They propose that consciousness itself may be fundamental, not emerging from matter, but giving rise to it. That perhaps reality is shaped by the act of being perceived. This is not the consensus view, but it is whispered at the edges, and it echoes something older, the idea that awareness is not an accident, but part of the architecture, that to observe the stars is not a coincidence, but a completion. If Earth was designed, then maybe that design was not finished. Maybe it unfolds, grows, evolves. Maybe the scaffolding is meant to be incomplete, an invitation to participate. A lesser-known model, loop quantum gravity, suggests that space itself is made of discrete loops, tiny grains of geometry that weave the fabric of reality, not smooth, but granular, not infinite, but countable. The very shape of space in this view is woven. Could we be part of that weaving? Could Earth and all it holds be one small stitch in a pattern we have only just begun to trace? If so, then the design is not in the stars or the atoms, but in the connections, the symmetries, the rhythms, not in what exists but in how it relates. And that's what scaffolding truly means, a support for something not yet complete, a structure for growth, a lattice for flowering. Perhaps Earth is not a product, but a platform, a place where physics, chemistry, biology, and mind converge, a space where reality hums not with perfection, but with possibility. Let's now drift to the edge, not of space, but of knowing. Not everything can be seen, not everything measured. Some horizons are not physical but cognitive. They mark the boundary between what we can understand and what lies just beyond. If Earth was designed, perhaps part of that design includes this very boundary, a veil that isn't meant to be broken but approached, not a wall, but a quiet fog. One mainstream truth in cosmology is that the universe has a cosmic event horizon. This isn't a horizon like Earth's edge or a line in the sky, it's a limit to what we can ever see no matter how long we wait. As space continues to expand, more and more of the universe slips beyond this horizon, its light stretched and dimmed into invisibility. The most distant galaxies we observe today are already racing away faster than light, not because they're moving through space at that speed, but because space itself is expanding between us and them. Eventually, even the closest galaxies beyond our local group will fade from view. A lesser-known implication: in the far future, cosmology may become impossible. Civilizations that arise trillions of years from now may see only a single galaxy. The cosmic microwave background will have redshifted into nothing. The traces of the Big Bang will vanish. The evidence of other galaxies will be gone. Their sky will be dark. Their models incomplete. If Earth was designed, perhaps part of that design was timing. Perhaps we live in a moment when the cosmos is still visible, still discoverable. A narrow window where ancient light still reaches us, where we can look up and remember what came before. But limits come in many forms. Another type of horizon is the black hole event horizon, a boundary around a collapsed star from which nothing, not even light, can escape. It marks a place where gravity bends space and time so deeply that paths turn inward forever. Anything that crosses the horizon is lost, at least from our perspective. And yet, black holes radiate. This is one of the great insights of modern physics: Hawking radiation. Over vast timescales, black holes slowly evaporate, releasing faint particles. This discovery bridges quantum theory and general relativity, and it raises deep questions about information. Where does information go when it enters a black hole? Is it destroyed? Or is it somehow encoded in the radiation? This black hole information paradox is unresolved. Some believe information is preserved on the event horizon, perhaps as holographic data. Others suspect it's scrambled, transformed, stored in ways we don't yet grasp. If Earth was designed, maybe such puzzles were placed not as barriers, but as invitations, challenges meant to stretch us toward new forms of thinking. Even here on Earth, there are horizons of understanding. Our brains evolved to navigate forests and rivers, not to grasp quantum tunneling or 10-dimensional geometry. We are meaning makers, pattern seekers. We see faces in clouds, stories in stars. That same impulse drives science, but it also limits us. We may never intuitively understand what lies beyond time, but we can reach for it. A lesser-known boundary in mathematics is Gödel's incompleteness theorem. It shows that any sufficiently complex system of logic will contain truths that cannot be proven within the system itself. There will always be statements that are true, but unprovable. In other words, there will always be something we can't know. This isn't failure, it's structure. It's a kind of humility built into the bones of reason, and perhaps if Earth was designed, that humility is part of the blueprint, A ceiling not of cruelty but of care, a way to keep the story moving, the questions open. Some scientists believe there may be ultimate limits to knowledge, not due to lack of curiosity, but because of the nature of the universe. Cosmic variance, the idea that we only have access to one observable universe, means we can never know what's typical. We can't rerun the Big Bang. We can't compare to other realities. We are in some sense confined to our one sky. If Earth was designed, then perhaps we are like seeds in a sealed garden, able to grow, to bloom, but not to escape. And yet, we have sent messages into deep space. We have sent machines to the edge of the solar system. We have built instruments to hear the ring of the Big Bang, to track the faintest pulses from dying stars. We ask questions about the multiverse, about dimensions beyond perception, and in doing so, we push the horizon, not by tearing it, but by listening at its edge. A lesser-known concept is the cosmic light cone, a model that maps what events in the universe we can observe or influence. Everything we do, say, or build radiates outward in a growing cone of possibility. Our past is shaped by what could reach us. Our future is shaped by what we can reach. And Earth, drifting quietly through that cone, becomes not just a planet, but a node of potential. We cannot know everything, but we can know this, that there are boundaries, that we press against them, that we are shaped by their presence. If there is design, perhaps it does not end at the boundary. Perhaps it includes the edge itself, the way a horizon makes us look farther, the way a silence makes us listen harder. The universe may always hold some truths in reserve, not as a punishment, but as a poem, a rhythm that never fully resolves, a chord that is never quite complete. We are not promised final answers, but we are gifted with the ability to ask, and perhaps, in the asking, we fulfill the purpose of the design. We return now slowly to where we began. Not to the beginning of the universe, but to the beginning of our question. What if Earth was designed? After drifting through galaxies and gravity, signals and silence, deep time and dark energy, we arrive once more at the blue world beneath our feet, and we begin to see it not just as a planet, but as a possibility, a place where ancient light finds soil, where chemistry becomes breath, where questions become life. Because whether or not Earth was designed in the way we imagine, it moves with a quiet coherence, a rhythm, a poise, a balance that does not shout, but hums gently beneath everything we see. It starts with gravity, holding oceans to stone, mountains to mantle, clouds to sky. Just strong enough to hold an atmosphere, not so strong that flight becomes possible. It holds the moon in orbit, shapes the tides, keeps time with every falling apple and every rising wave. Then, light. The sun radiates energy at just the right distance, through an atmosphere that filters the harsh and lets in the nourishing. Photosynthesis hums in leaves, fuels ecosystems, carves forests from sunlight. Light does not just illuminate, it animates. And air, a soft envelope of nitrogen and oxygen, tuned to support breath, regulate heat, and scatter the blue of the sky. A medium for birds to glide, for sound to travel, for fire to warm. Too much, and it would crush us. Too little, and it would let the cold of space spill in. Water again and again shapes everything, flowing in rivers, frozen in glaciers, cycling through clouds, whispering through cells. It connects all things, whether to ocean, soil to root, cloud to stone. It is both source and solvent, both rhythm and rest. And beneath it all, the Earth itself, tectonic plates shifting just enough to recycle carbon, stir evolution, reshape continents. A core that generates a magnetic field shielding the surface from solar wind, a moon that calms the tilt, a sun that burns long and slow. We might say these are coincidences. that life evolved to fit these conditions, not the other way around. That we are here because we can be, and had things been different, no one would be asking these questions. That's one way to see it. But there is another way, to see Earth not just as habitable, but as hospitable. Not just fit for life, but welcoming to it, gentle in its cycles, resilient in its balance, complex in ways that enable simplicity, simple in ways that give rise to complexity. A lesser-known example of this hospitality is the stability of the sun's output. Over billions of years, its luminosity has increased slowly, allowing lifetime to adapt. It is not a flare star, not a variable sun. It burns with patient consistency, as if keeping time for the evolution of thought. Another is Earth's magnetosphere, powered by a molten spinning core. It deflects cosmic rays, channels solar storms, protects DNA. Without it, our atmosphere might have been stripped, like Mars. Our oceans boiled away, our chances erased, and then there are the colours. The deep blues of ocean, the ochres of desert, the greens of forest. Not every world reflects light this way. Earth's palette is the result of scattering, absorption, reflection, physics sculpted into beauty. We don't know if beauty matters in the grand scheme, but here it does. And beauty, like breath, is not a necessity, it is a gift. If Earth was designed, then perhaps it was designed not as a machine but as a story, not efficient, not flawless, but unfolding, layered, rhythmic, told in gravity and wind, in rivers and roots, in nebulae and neurons. Perhaps design does not mean control. Perhaps it means invitation, an invitation to wonder, to participate, to care. Because Earth, in its quiet way, seems to want to be noticed, not just with instruments, but with affection, with awe, with a kind of noticing that becomes gratitude. And here we are, at the end of our drifting journey, 20 sections, tens of thousands of words, countless stars and questions, and we still do not know. Was Earth designed? We cannot say. But we can say this: it feels held, it feels balanced, it feels listened to. Perhaps the answer is not binary, not yes or no. But how we carry the question, whether we treat the world as sacred or accidental, whether we live as stewards or passengers, whether we notice the quiet design in each raindrop, each seed, each breath. Because in the end, design is not only about origin, it's also about what we choose to do with the gift. And now, as our journey eases to a close, let us settle into stillness. Let the stars dim in your mind's sky. Let the distant light fade into velvet. Let the questions rest for now. We've wandered far tonight, across the folds of space, the drift of time, the scaffolding of galaxies. We've watched particles dance, oceans breathe, moons tug, and minds awaken. We've looked gently at the possibility of design, not with certainty, but with a sense of listening, a readiness to wonder. Earth remains, just as it always has, spinning slowly under a sheltering sky. Quiet rivers still move toward the sea, trees still reach toward the sun. Starlight still falls through the darkness like dust in a beam of light. And you, resting here, listening, breathing, you're part of it all. You're the witness, the vessel, the momentary mirror of a vast and patient universe. You don't need to know all the answers. You don't need to hold every truth. You only need to rest in the rhythm, to feel the quiet weight of time, to breathe as Earth breathes, to exist softly between light and shadow. Perhaps that's the purpose, not to solve the cosmos, but to feel it, not to own the stars, but to be touched by them. So let your body relax, let your thoughts settle. Let your breath rise and fall like a tide guided by the moon. Let your dreams be full of oceans and orbits and the warmth of quiet light. And if the universe is listening, as perhaps it is, May it hear you now, resting in peace. Good night. Sleep well. You are home.